All right, welcome. So in this video, I want to continue our series on recursive algorithms and recursive analysis. And we're going to take a look at another algorithm that we've already looked at in an iterative setting, which is the search algorithm, just searching for an element in a list. But now we're going to carry this out recursively. So again, just to refresh ourselves of the problem at hand, we looked at this earlier when we were talking about analysis of looping structures. So we have an input list, a list of integers, in this case n integers, possibly empty, we haven't stated that here, but 0 to n integers here. And then we want to output either an index of the integer that we're searching for, or -1 if the integer we're searching for is not found. The integer we're searching for we usually call t for target. But otherwise we're just looking for this index, again, as I mentioned, or -1 is just the error code that we'll use if we don't find it. So again, we took a look at a way to solve this iteratively, meaning with a loop, and maybe that's where our instinct is. But we can also do this recursively, which is something we might have to do if we're in a language that doesn't have looping structures and only has recursion as a way to iterate. So if we want to think about how to search recursively, we really are following the same strategy that we would do iteratively. That is, we have to break it down. We don't sort of do it all at once. We're going to do it piece by piece. And just like iteratively, we might say, well, let's look at one element at a time. The same thing is true recursively. And the same choices are sort of before us. In the iterative, we might say, well, if we're going to look at it one at a time, well, what order do we go in? Do we start at 1, go to n? Do we start at n, go down to 1? Do we do something weird that's not one of those two? All of those are correct in the sense that they'll all get us to the right answer as long as we look at all the elements, right? Same thing recursively. We have the same choice in front of us. But now the choice is a little bit more, well, which element are we going to look at first? That's the way I want to pose it when we think recursively. Because the way that recursion works is iteratively we plan out maybe the whole trip. We say, okay, I'm going to do 1, and then I'm going to do 2, and then I'll do 3, and all the way up to n. Or maybe I'll start at n, I go back to n minus 1, and so on, all the way down to 1. We kind of plan it all out. Whereas recursively, what we usually plan is just our current step in the trip, and we kind of trust that when we get to the next step, we'll figure that one out too. So in this case, we might just pick one element that we're going to use to compare, and then we'll recursively search the rest. And that's where the trust comes in, saying, well, we'll recursively call the rest, meaning we'll trust in ourselves effectively to do the work in the recursive call that will solve the rest. So that's sort of the choice we're going to make here. And again, if the choice before us is just which element should we look at first, again, we get a couple different choices. Which element should we look at first? A1 stands out as a great candidate. Also, AN stands out as a great candidate as well. What about A2? We're not guaranteed that A2 is there. Okay, A1 we're guaranteed to be there if the size of our list is at least 1. AN we're guaranteed to be there if the size of our list, is at least 1 as well. Why is that? Well, because if our list is of size 1, then n is 1, so AN would be there. But A2 will only be there if our list is of size 2 or greater. And that might be something we can put into our algorithm to check. As long as we have 2 elements, always pick the second one. Or as long as we have 10 elements, always pick the 5th one. I don't know. There's lots of different algorithms we could develop here. A lot of the ones that we could come up with could even be correct, meaning leading to the right answer, and maybe even as efficient as ours. But sometimes when we have competing algorithms that are, all correct and also equally efficient, we usually just go for the simplest one or the most obvious one because, geez, that's simplest for us. Okay, so in this case, again, I'm going to default to picking, well, maybe I should pick the first element, or maybe I should pick the last element. And here's the truth, I don't remember what I put on my slide, so let's see. Okay, so I had a hypothesis here, which one I might pick. Why would I pick 1, and why would I pick n? Maybe I'll fill that out when we get there, but we can see here that I picked n instead. But let's look at the recursive algorithm that I've come up with, remembering that in a recursive algorithm, the first thing that we're going to do is we're going to want to check for some kind of terminating condition. Now in this case, our terminating condition is going to be if we don't find the element or if we find the element. We sort of have two cases that we can get. The one that I'm going to consider first is really a bit of error checking maybe. So we'll notice this first bit is what happens if n was 0? Then we can't even pick out our a sub 1 or our a sub n, because remember when we were discussing that conditioning above, we said as long as the size of our list is at least 1, then we know those elements are there. Well, if the size of our list is 0, if n is 0, then well, the correct answer is just 0, is just minus 1, is just there is no target element in our list. So we're going to tackle that one first, and often when you have more than one terminating condition, this is also true for recursive conditions, you're going to want to be careful about the logic and what order you compute them in. In this case, it's important for us to maybe do this line before this one, maybe not so much in our pseudocode as it is in our in actual code. Down here we might get an out of bounds error if we try and find an element that isn't there. Okay, so if there is no element there, then we should return -1 before we try and check that element. However, if the size of our list is not 0, it's greater than 0, then we move on to the next line. And the next line just checks this element. Now again, I mentioned which element we look at is the choice that we have available to us in this algorithm. Do we look at the first element? Do we look at the last one? I chose to look at the last one. Now, the reason I chose to look at the last one is the same reason I mentioned in my previous video, in the last video, which is I'm thinking more about analysis, and I want to think about the size of this sub-problem that I've created over here. And it's very clearly of size n-1 the way I've written it here, because I broke off that last element, the a sub n, and took it out, and it used to be of size n. Now if I had broken off the first element, I would have had to write here a sub 2 up to a sub n, which by the way is a perfectly good algorithm, and it might be the more intuitive one, natural one we reach to. But the reason I didn't particularly pick that one this time is just because I would have had to do one extra step of math and said, well, how many elements are there from 2 up to n? And guess what? The answer is the same, n-1. This one just makes it very clear. So that's a very subtle choice, but I just wanted to justify why I made this choice. Why did I pick an instead of a1? I just liked how it made my math nicer over here. Okay, and if you don't like that, if you thought, hey, I like picking the first one, first ones are first, great, that's a good reason to go that way too. Okay, and you'd have the same size of a subproblem over here, which is all that's important to the runtime that we're going to get to in a second. The correctness, hopefully we're all pretty comfortable here. Well, let's see, we didn't quite go over this last line here. We said if we find the target in element n, we'll just return n. Good, that satisfies our output correctly. But then we just trust in the recursion. We recursively call on the smaller list now, searching for the target, trusting that it would find it if it was there. Now let's just be careful and maybe run it through our internal brain compiler here and make sure that works, and say, well, what would happen next? When we plug it in the next run, we don't have a sub n anymore, we have n-1. When we did that, when we get down here, the next one we would check would be a n-1. If we find it there, we return it. Otherwise, we get one smaller again and one smaller again, eventually getting down to just a2, a1. If we don't find it on a1, we would shrink down one further just to the empty list, which gets us to our terminating condition here that says, nope, we didn't find it. Good. That's what our correct output would be if we go through all the elements and don't find it. So hopefully we're all on board that this recursive implementation of search is correct, but let's see if we can put in a little bit of analysis on it now. Okay, so how many operations? Now remember, we're going to kind of go line by line, but really when we think about recursive analysis, we want to be splitting ourselves into our cases. What are we talking about here? Are we going to be entering into the terminating case, or are we doing recursion? Because in our analysis, remember, we're going to make this recurrence relation. This recurrence relation is going to consider those in separate portions of the recurrence. And so usually I start, as I do with most things, it's a good strategy in computer science to start with the easiest thing. This is when we're doing divide and conquer. If you've divided things into different chunks, pick the easiest one to start with. And in this case, the easiest one is usually the terminating case. We actually have two terminating case in the search algorithm, and that's because we actually have a case of early termination, at least the way we've written it right here, which is in the case where we find the target somewhere along the way. It might be an AN or in one of our recursive calls along the way. When we actually do find the element, we can consider this as being early termination. We haven't had to search through all the elements to get there. We happen to find it, luckily, and that allowed us to terminate early. I'm not going to consider that because if we're wearing our worst case hat, remember, when we're doing analysis on an algorithm, we're going to have different caps on, and sometimes we'll want to look at the best case. The early termination is exactly what we want to look at if we're talking about the best case, in which case we would say the best case of finding our element, of course, is finding it in the very first place we look, right? That's lucky. The worst case when you're looking for an element is you find it in the last place, okay? Now, of course, there's a sort of common knowledge that you always find the thing in the last place you look because you stop looking, and that's what this whole idea of the early termination is that once we find it, we stop looking, okay? But for us, considering the number of operations we carry out, then the worst case is going to be we find it in the last place we look, and the last place we look is in the last place in the list, in this case, which is element 1, because that's the last element we would look. That's if we were finding it. But the other worst case in this particular algorithm is if we don't find it at all. And usually that's what we treat as the worst case when we're thinking of a search algorithm. The worst case is often when you don't find it. What happens when it's not even there? Because of course, if you're looking for something and it's there, we get the luck of finding it, and as I mentioned already, the early termination. But if it's not there, usually the only option we have in a search, usually, unless we've got other information we can bring to bear, is to look in every location. And that is what we call an exhaustive search, because we exhaust all the locations it might be, and exhaustive searches are often exhausting in the sense that they take a lot of time and effort. And so if we can ever escape that, then we would like to. Now, this search that we're looking at here is indeed an exhaustive search. This is sometimes called a sequential search. It's sometimes called an exhaustive search or a brute force search. In this case, we're calling it recursive search because we're carrying it out recursively, but it is also an example of an exhaustive or a brute force search. Okay, so since we're trying to figure out how many operations we're carrying out here, and I mentioned we're going to be doing the simple case, the terminating case here, and I'm going to ignore the early termination. So it depends who you want to argue with about this. I'm not going to try and put up too much of a fight. If you think that the worst case here is going to be exiting on line 2 for your terminating case or base case, go right ahead. I'm going to treat it as exiting on line 1, which is our worst case, which is when we've exhausted all of our elements. Now, let's see how that works. Again, in terms of counting our operations, we're going to enter the method with our method call, our function call. That's one operation. 1 for the check here is n equal to 0, and then 1 for our return. So I'm going to count that as 3 operations for the terminating case. But then for our recursive case, we're going to skip over that second line. That's the early termination. It's our best case in this case. If n is greater than, in this case, this is n is 0 is the base case that we've considered now. If n is 1, we could do this case or the recursive case. Or if n is greater than or equal to 1, we could do either of those cases. But this line 2 here, represents the best case for this n greater than 0 case that we're considering here because it's early termination. And notice it's a constant. Let's just check what that constant would be. It would be 1 method call, 1 check here, but not this return statement, because if this check is false, if we're greater than 0 here, we enter this line. Now this is an else if, so that is another check. So let's say again, we did 1, 2, 3 now, and if we're exiting on this line, it would be 4. So if you disagreed with my assessment earlier, and again, you're perfectly valid and could be correct in doing so, then you might want a 4 here instead of a 3. In the end, that usually doesn't change a lot, but if it matters to you, then let's put it in there. Now, that's if we exited on this line, but I'm saying we're not going to exit on this line. We're entering into the recursive line now. So, entering into the recursive line, we did 1, 2, 3 checks to get here. Now, let's see here. This is an else, but it's not an else if, so we don't do another if. We have the return, and we have the arithmetic as well. So we did 1, 2, 3, 4. The arithmetic here is the -1, 5. Okay. Plus whatever effort we put into this recursion. Now, remember, just like we're trusting in the recursion to do the work for us here, we're trusting in the recursion here in our analysis as well, saying, well, we are expressing this as a t term, our recurrence relation t of n. We can express the cost of this call, not the arithmetic, not the actual -1 we do to do this, but the whole call as tn -1. So we'll have one recursive call of size n-1 plus the 5 pieces of arithmetic that we did. So I mentioned the 5 operations and then the recurrence relation that we come up with here. Now notice a slightly different from the last recurrence relation, because in this algorithm our terminating case actually is n equals 0. That comes out here in our recurrence relation as well. Now, if we actually change this to a 1 and a 1, is that going to change this recurrence relation? Not in its asymptotics, not in its big theta, its big O, and its big omega. It may change it in its, or it will change it, I shouldn't say may, it will change it in its actual output, but that difference in output will only be by a constant. And again, remember, as computer scientists, we usually we're going to try and ignore as many of those constants as possible when they don't matter to us. Okay, so let's see if we can explore and express this in a little bit more detail and find out what its closed form expression would be. All right, so as we did in the last video, let's just try and plug in some values and see what we've got. Now in this case, we actually start at 0, so I'm going to start with 0, and we're going to see that t0 is actually just 3. Well, of course, by definition, it's 3. That's an easy one to figure out. Let's do our next one then. T1 then would be T0 plus 5. So T0 plus 5, T0 we just said was 3, so that's 3 plus 5, that's 8. Okay. Let's go again. What about the next one? If we remember the last video, remember sort of how the pattern emerged last time. This one is going to be the same. We're going to get T of n minus 1 again, so this will be T of 2 will be T of 1 plus 5, so we get another 5 on there. We got a 13. Okay, 8 plus 5 is 13. So again, we might see the pattern already. Another 5 is going to pop out. We'll probably get 18 as our next line. So can we take that and turn that into a formula that's not recursive? So again, maybe can you eyeball it? I think I know it. Now it's going to be similar to what we did last time, but be careful about your indexing a little bit. Make sure you don't get your off by 1 off. Okay, now last time there was an n minus 1 in there. I don't think the n minus 1 is going to show up this time because we start at 0. Okay, that is, when t was 1, we had 1 copy of 5. And when t was 2, we had 2 copies of 5. And when t was 3, when we were t of 3, we had 3 copies of 5. So the number inside our argument, which is our n technically, is going to determine how many copies of 5 we get. So what does that mean? We should write this as t of n would be equal to 5 times n plus 3. 5 times n plus 3, or 3 plus 5n is same idea here. The 3 here, just the number, the copies of the 5 is determined by whatever argument we have here. Now, of course, this is much easier, simpler. That we can, we can prove a big theta bound on this and say this is big theta of n. But I just want to prove that this math that we did here, this is sort of a guess that we got here. And sometimes we can mess up our patterns if our patterns are a little bit hard to see. So I want to prove that it's correct using induction. So let's do that. So let's attempt to prove that this is true. And we're going to do that again using induction. So this is more a practice with our recurrence relations with induction again, just to see if we can practice those skills and build them up. So again, our proof by induction, we'll do induction on n. So we'll start with a base case. In this case, I'm going to select base case n equals 0 because that's where we start out here. So our base case of n equals 0, what do we need to prove? We need to prove that t of 0 is equal to 3 plus 5 times 0, or 3. Well, guess what? T of 0 by definition is 3. So again, t of 0 by definition is 3, which is equal to 3 plus 5 times 0, which is this formula with 0 plugged in. So again, as I mentioned in my previous videos, usually when I get to this stage of the base case, because this is so obvious and I feel like I really haven't done anything yet, I usually just put a check mark there. It's like a pat on the back and say, good, I did it. Okay, I got. And you're really just kind of verifying that this is true, and usually it's easy to do so. So yeah, when you're done, just check it off, mark it off. Every once in a while there will be a condition here, a little point that you need to remember. So sometimes the check mark for me is also just a reminder to check, is there something I need to double check here? In this case, this works for all values. There was nothing we needed to assume to make this to work, so we're good. This works all the time. Check mark is all we need. Okay, on to the next step. So if the base case, again, is usually the easy case, it's sometimes so simple, it's just a matter of checking that something is true. So then the next step, the more complicated case, begins with writing down our inductive hypothesis. Now, I mentioned this in the last video. I've shifted the way I'm going to be writing here. Instead of doing my induction by assuming it's true for n, and then talking about n plus 1, which is, again, a legitimate way to do induction, I'm going to talk about making an assumption about n minus 1, and then making an argument about n. Both of these are legitimate ways to finish the inductive step, and the reason I'm pivoting to this approach is so that in a moment, that is in a few videos, we can start doing strong induction, which is a more powerful form of induction. So again, let's restate the inductive hypothesis here using n minus 1 instead of n. So what I'm going to do is plug in n minus 1 into my theorem here for n. Okay, so instead we'll have t of n minus 1 is equal to 3 plus 5n minus 1. Okay, so basically all that's doing is saying, assume that it was already true for the last value. In this case, the last value is n minus 1. And now we're going to go on in our inductive step to handle n when n is greater than 0, because we already handled the n equals 0 case here. So we'll do on our inductive case, n is greater than 0, and now we want to prove that for t of n, it's going to be equal to 3 plus 5n. What do we know? What can we bring to bear on that? Now remember, the first two steps in our inductive our inductive case here, are always the same. The first one is apply the definition. What do we know about t of n? This is the definition of t of n. That's why I've got it written here up above. So let's record it down. Now, we're in the case when n is greater than 0. So this row doesn't matter. It's the second row that matters. T of n is equal to t of n minus 1 plus 5. That's how we start off our math. Okay, t of n is equal to t of n minus 1 plus 5. By definition, again, sometimes I write comments for myself. I might write a little comment here that says, by definition. Okay, the next step, the second step, is also always the same, which is usually by definition, we've got something we don't like in there, which is this recursive term, this t of n minus 1 term. But our inductive hypothesis, if we've done it right, has been set up exactly so we can replace that term. It says, assume that this is exactly equal to this. Well, that means we can replace our t of n minus 1 term with the 3 plus 5 times n minus 1 term. So the next line is substitution. Boom. We swap it out. Now where are we? I said the first two steps are always the same. The next however many steps are always the same too, which is now it's algebra. Now we do algebra, and it should get us where we're going. Okay, at least for these easier first examples. Okay, So algebra should get us where we're going. So let's just, look ahead. Multiplying my 5 through, I'll get a 5n times a minus 5. The minus 5 cancels out. Looks like I'm on the right track. So let's go through the process. 5 multiplies through. We get the 5n and the minus 5. These two are going to cancel out to give me 3 plus 5n. That's what I was aiming at. So check. I need to put another check saying I'm done. I got where I want to go. Now, I'm not completely done the proof because usually I at the end I put what I call my inductive post-amble, where I just say, hey, I'm done. I've actually done induction now and I'm done. So I just say, by induction, I've shown what I wanted to show. Okay, and then I throw my little square, my little box for my QED, and tell my readers I'm done. Okay, so again, as I like to set up my proofs, I like to say, okay, theorem, proof, here's how I'm going to do my proof. I tell my reader what I'm going to do, then I do it, then I tell them that I did it. Okay, what I'm going to do it, and then tell them that you did it. Okay, that brings us to the end of our analysis of the recursive search algorithm. So thanks a lot for watching, and we'll see you in the next video.